Okay, good morning. Hello. Let's start. So, welcome to already the last lecture in statistics for data science in the winter term. So the last topic we're going to discuss is variational inference. Maybe we finish it today, maybe we need another hour, I'm not quite sure. But together with support vector machines, this is then the 16 lectures you got in statistics for data science. Yeah, and the topic is variational inference, which, as I mentioned last week, you can also see as another way to do approximate Bayesian inference. So we're still in the Bayesian inference scenario of things, and we want to find a way to do Bayesian inference in the not necessarily conjugate case. So in the conjugate case, we can compute the posterior distribution calculate better the posterior distribution analytically. And we will see a couple of examples for that today in the Übung. Then last time we discussed numerical methods, specifically to approximate integrals that are often required, for example, as the normalization constant of the posterior distribution. Today variational inference as another way to do approximate inference, but usually not based on sampling. Although we've seen last time that also these numerical integral approximation methods don't necessarily need to be sampling based. I've been working or studying and contributing very little, but a little bit, to variational inference, I guess, for 10 years now. So it was the big thing for my postdoc after my PhD. So I wanted to learn about variational Bayes. Motivation there was that brain imaging people, specifically Carl Friston, says the brain does variational Bayes, and that's called free energy principle. So I wanted to know what variational Bayes is. The other thing why I wanted to know more about variational Bayes, because it's a very general framework, and basically all parameter estimation schemes in statistics can be considered special cases of variational inference or variational Bayes. So maximum likelihood, restricted maximum likelihood, EM algorithm, they can be shown to be special cases of this. So in a way, once you are happy with variational inference, you are happy with a lot of statistics, at least statistical inference. And the other thing that I'm also interested in, or became interested in variational Bayes, because it's quite a modern technique, and it's novel in a way. So where numerical methods for Bayesian inference were developed kind of in the 50s, 60s, and so on. So after the war, variational inference started early 90s, late 80s, something like this, but then really became established more around 2000 or so, I guess. So that it was really a thing, and is still being developed. So for example, all these optimality criteria for maximum likelihood estimators that you can establish are by far not established for variational inference yet. So it's modern, it's still under construction if you want, and but it's also very general, so understanding it helps to understand a lot of things. And luckily it has also survived the neural network resurgence in machine learning around 2010, where people, of course, in machine learning you have always not tension, but you have people that work statistically, so probabilistically, based on probabilistic models, and you have people that work like engineers or whatever, so they don't really care what the model is, and neural networks are obviously usually probability free, but it has been saved into at least in machine learning, by this idea of variational autoencoders, which we will not really discuss in detail, but it's just variational based essentially. And at one point you plug in a neural network so that all the neural network people are happy, but it's variational inference. So it's still there, it's still alive, although I was worried a little bit like a couple of years ago whether it will die, but it hasn't died, it's still there, and it hopefully will remain. So that's variational inference, short history. We did a little bit on that, and yeah, a very good starting point if you now learn about it, or let's say a good starting point, is this review by David Bly. David Bly is a machine learning guy from the US, I think he's at Columbia, and he has he's also contributed to keeping variational inference alive. So this 2017 is called a review of variational inference for statisticians, which also emphasizes that variational inference grew a little bit more out of machine learning, but also neuroimaging. Neuroimaging has also contributed a little bit, and to science in general, not only to the careers of neuroimagers. And in this review, he introduces variational inference, or they introduce variational inference, and then emphasize that there's still a lot of work to do in terms of understanding variational inference better and establishing its properties, essentially. So that's a good starting point. But there are also many other variational inference tutorials, one of them being ours from a couple of years ago. Good. So the stuff that I then want to talk about is first the basic story of variational inference, so the foundations of variational inference. So what's the problem that is being addressed with variational inference, and how is it being addressed? And then it will hopefully get clear that variational inference is like maximum likelihood estimation, a general principle. So maximum likelihood estimation is a maximized log likelihood function to find parameters. That's a good idea, or it's an idea, let's say. And also we've seen that's actually a good idea if you look at certain properties of maximum likelihood estimators. But it doesn't tell you in detail how to do maximum likelihood estimation for a given model that you have. It gives you a recipe, that's true, but you still have to specify, for example, the log likelihood function if you want to maximize it, and then think about how you want to maximize it. And similar with variational inference, it's a general idea, a general algorithm if you want, but in a concrete example and for a concrete model, you still have to figure out how to apply it. And then the second and third things are two applications of variational inference to a Gaussian gamma model and a nonlinear Gaussian model. And these applications are rather brief because they involve analytical derivations, but I didn't put all of these analytical derivations in, so they then serve more as showcases of how variational inference can look in practice without going into all of the derivations that are necessary to then establish these things. But we will come to it and see it. Maybe before we talk about the foundations of variational inference, about the name variational. So this name variational derives from the calculus of variations, which is like standard calculus, a field of math that looks into how to maximize functionals, or that's the old name, or functions of functions. So if you have a function that is a function of a function, and you try to find the maximum of this functional, you basically can establish similar criteria like for maximizing a function of numbers, so a function of real numbers or vectors. So you can establish derivatives, and then so in this case then the derivative of a function with respect to another function and set to 0 and so on. And there is important functional in variational inference, which we will later see. It's called the evidence lower bound, or some people call it the variational free energy. I used to call it the variational free energy. And this function needs to be maximized. And because this is a general problem in variational calculus, this form of inference has been called variational inference. Now, the way I will present variational inference here doesn't require variational calculus at all, because the only thing where you actually need variational calculus is for a very general theorem of how to maximize this specific functional, but you can show the solution without ever talking about variational calculus, as we will see. So the variational in variational inference, due to variational calculus, maximizing function with respect to functions. Interesting in control theory and a nice generalization. Has anyone studied variational calculus? You see that in functional analysis also. But functional analysis it relates to calculus of variations, like a little bit like real analysis relates to calculus. So in calculus you compute things and you get solutions, and in real analysis and functional analysis you establish the theory behind it and the assumptions that you need and so on. So yeah, anyway, that's where this variational comes from. It's not variance, doesn't have to do anything with variance. And a little bit the problem is now, as I will present variational inference, and it's how it's typically presented, you also don't see the variational calculus bit of it. So it's just a name in the end. Yeah, that's the little story about the name. Good, then let's get started. So I define here what I call the variational inference problem. And this variational inference problem you can also just view as the problem of Bayesian inference if you want. Always rests on a probabilistic model. So we assume that we have a set of observable random variables x, and we have n of them, for example, n data points, but not necessarily. We have a set of latent random variables z, so z1 to zm. These could, for example, be parameters so one parameter that is related to all of the data points, or it could be a latent state that is related to each of these observations, like in state space models. So we are not specifying these things further for now. Later on, when we talk about examples, there of course we make things more concrete. Here we just assume that we have these observable random variables for which we can acquire data, and we have these unobservable or latent random variables which we can only indirectly observe by means of the data. And we assume that we have what I would call a probabilistic model, so a joint distribution, better actually mainly what we are doing here, a joint density. So I think in the Bly review they talk throughout about densities. So this would be probability densities. I think that's a little bit restrictive, because you can also have probability mass functions here. But I think so. Definitely, it's if you commit to densities, I guess you are more on the safe side. So if you think about densities, that's fine. You can also think about distributions. But so I wrote a little bit about in the 2016 paper, in the appendix, I tried to write down a mass theoretic foundational description of variational Bayes or variational inference, because we wanted to show that restricted maximum likelihood is a special case of variational inference, and then you get into entropy things, and then you have the problem with entropy that anyway, so it's, let's say, another way to say it is that With densities, you're on the safe side, and if you want more, so if you want both mass functions and density functions to work in variational inference, you would best have a measure theoretic formulation of variational base, but you will be hard pressed to find that in the literature, which has to do with the fact that it's not mathematicians working on variational inference so far, but mainly machine learning people and maybe more and more statisticians. So think about these things as densities, then you're on the safe side. The problem of variational inference is then to approximate, ideally to approximate correctly, the conditional distribution of the latent variables given the data. Which is, of course, you can also just call the posterior distribution in this probabilistic model, and the log model evidence, which is the log of the marginal distribution of the data. Yeah. So you should always so one way you can always think here is now X is data, like X was always data, and Z are parameters. So here you want to have the probability, the marginal probability of the data under the model. So you integrate out the latent variables, so the parameters, and here you just form the posterior of the parameters given the data. So essentially the variational inference problem is just the problem of Bayesian inference. The one thing that is maybe of interest here is that we will actually solve both problems. Why do we want to solve this? Of course, the posterior or the conditional distribution we can use to do parameter inferences. We can summarize this and get Bayesian estimators and so on. The log model evidence, as we've seen briefly when we talk about general Bayes, we can use as a model comparison criterion. So yeah, we can evaluate the probability of some data under a given model and compare that with the probability of other data, of the same data under a different model, and then say we like this or that model more. So we address both essentially parameter estimation and model comparison in variational inference. Why do I call it variational inference problem here and not Bayesian problem? I don't know. I just want to make the important. So essentially, variational inference addresses Bayesian inference, but both posterior evaluation and data marginal evaluation. And of course, you can also, from these things, compute then other things, right? So you can also compute, for example, the posterior predictive distribution by looking at the conditional and then using this together with the likelihood to get a predictive distribution. So everything that you can do based on the posterior distribution, you can of course also do based on the solution of the variational problem. Yeah, so this is what I said. Variational inference and variational Bayes essentially are the same thing. The thing is, with variational Bayes, of course, you bring in this business of Bayesian statistics, and then people are like, oh, what about the prior? And if you say inference, then they maybe don't pick up immediately on the Bayes scenario. Also, these specific special cases, for example, that maximum likelihood can be shown to be a special case of variational inference or of Bayesian inference in that case, is better described by the term variational inference. And yeah, I think I just like the term variational inference by now a little more. It's also more the modern term. That's what I said. The latent variance can be parameters or latent states, and yeah, usually this joint distribution is described in terms of a PDF rather than a PMF. That was that. Any questions about this? So this is what we want to solve. So we want to essentially, so we specify a probabilistic model, so a joint distribution of all observable and non-observable or latent random variables, and we want to, we know the likelihood, we know the prior, because that's how we always start Bayesian inference, and now we want to evaluate the posterior and the marginal log likelihood. And of course, you can also compute the exponential of that, and then you just have the marginal likelihood. We will see in a second why. Here we have the log. Good. So the most basic thing in variational inference is that the log model evidence can be decomposed into two numbers. So the way you should think about this log model evidence is, of course, in two kind of ways. So you either consider the x fixed, then this is a sort of data point. Then, of course, the density value associated with x is fixed, and then you compute the log, so that's a fixed number. The other way you can view this is, of course, that this holds for all of the x's. Yeah. So this is just you should always keep in mind. So when we talk about what this means here is that we have the log model evidence. You can view as we have here one number 10. And we can always decompose that into two other numbers, for example, 4 and 6 or 7 and 3. So of course here we will make it more concrete, but for looking at this equation, you should see one number that we split into the sum of two numbers. What are these two numbers? Well, first of all, they require what is known as a variational distribution, and it's usually denoted by Q. So QZ is a distribution over Z. For now, it's an arbitrary distribution. It's similar to the conditional distribution of Z given X in the sense that it is a distribution over Z. Yeah. So if Z, for example, is a two-dimensional vector, then of course the conditional distribution of Z given as a specific value of X is a distribution of a two-dimensional entity, real numbers, for example, and Q also needs to be a distribution over Z, so a two-dimensional real vector in this case. For now, this QZ is any distribution, arbitrary distribution. And then we have two numbers here, namely the evidence lower bound, and usually now abbreviated ELBO. For the brain imaging people, this is the variational free energy. ELBO, evidence lower bound, then I like the name more because it's clearer about its role in this context, which we'll see in a second, and it's not as mystic as free energy, because what is free energy? And the other number is the KL divergence between this arbitrary distribution QZ and the posterior distribution ZX. So this is actually the distribution that we want to evaluate. Now, what are these things? So the ELBO, which we view here as a function of QZ, is this integral. So you take you divide the joint distribution or the joint density that you have specified by the variational distribution, take the log and integrate over by multiplying with QZ and integrate over Z. Note that the ELBO, of course, if you have a specific data point, also depends on the specific data point. So if you observe for X, for example, if it's a single number, you observe 10, this will come out different than if you, for example, observe 20 or so. But the important thing is that we view this as a function of QZ, so we can change the ELBO by changing QZ. And here you already see this kind of variational calculus thing. So the evidence lower bound is this integral, so this returns a number, but what you put into it is a probability density function. So if if the posterior distribution here is encoded in a or is given represented by a PDF, then QZ is also a PDF. Why this definition looks like that is actually determined not so much by it itself, but by the KL divergence. So the variational free energy, or the elbow definition, is like that because the KL divergence is like that. And we will talk a little bit more about the KL divergence. I assume some of you have seen that. So the KL divergence between two probability density functions over the same random vector, random variable, is often notated like this. It's so as you see, I also don't write the elbow as a function, because then I would have to talk about what function, what's the domain of the elbow is, and that's of course the set, in this case, of probability density functions. So I would have a function space. The KL divergence is defined on a tuple of probability density functions, and one could just view as a function of two arguments, two probability density functions. It's classically notated with these two bars. They don't have any specific meaning, and you actually never see them besides the KL divergence. So, but then it's also not unhelpful, this kind of notation, because you always see that the KL divergence is between this and this. The KL divergence is defined like that. I think there's one thing that needs to be satisfied, because we cannot compute the log of 0. So if you go into the mathematical definition of the Kuiper-Gleiberg divergence, you have to be a little bit careful in terms of the of non-zero things here in the log, but roughly it's like that. So you have this ratio, you have the log of it, and you evaluate the integral over qz. Yeah, and we will look at the KL divergence a little bit more in a second. Some remarks. QZ is called variational distribution if these QZ have parameters. It's sensible to call these parameters of the QZ distribution variational parameters, because they refer to the variational distribution, and often we have many parameters, and then it makes sense to distinguish them. And as I already said, the evidence lower bound is sometimes called variational free energy, and we will not talk about why it's called free energy. You can talk with Felix Blankenbach about this, not with me. I tried that for years to get that out of his head. Anyway, so maybe before we look at this, let's have a look at the Kuiper-Gleiberg divergence. Who has seen the KL divergence? Okay, so the KL divergence is between two PDFs, QZ and PZ, and these are now arbitrary. It's general, it doesn't have to do with, in the case that we are looking at, is defined like that. So that's the same definition as before, and it's a basic measure of the divergence, or let's say the non-similarity, that's maybe one way to say it, the non-similarity between these PDFs Q and P, in the sense that, or dissimilarity, in the sense that if the PDFs are exactly the same, take on exactly the same values for all values z, then this dissimilarity is 0. They are not dissimilar, they are similar. And if they are dissimilar, so if they are not, sorry, if they are not the same, if they are dissimilar, then the KL divergence is larger than 0. And this is a very important property, that the KL divergence between two probability densities is always larger or equal to 0. Actually, we could take the this is larger.
Actually, the condition for the equation in the middle, equals 0, can be strengthened to as almost everywhere QZ equals PZ almost everywhere.
I guess, yeah. Yes, if you say so. So like I said, so one can be more subtle about the definition of the KL divergence. We don't go into these subtleties because the rest of variational inference is not that subtle yet. So the KL divergence is studied much more than variational inference. So there are measure theoretic foundations of KL divergences and entropy and so on, but variational inference not yet. So the most important thing from our perspective is that the KL divergence is non-negative and it's zero only if the two PDFs are the same. These properties we will discuss in the Übung. So KL divergence is a general thing. I think we used it a little bit already in our proof of the maximum likelihood optimality stuff. It's not a metric. This is always where mathematicians start shouting at one point. So when one says it's a measure of distance, then you have the mathematician in the room shouting, but it's not a metric. And then you say, yes, it's not a metric. It actually, the way it was proposed originally was as a metric for this, because it's not symmetric. If you add the two, then you get a metric. From our perspective, the most important thing about the KL divergence is this notion of dissimilarity, and this I've shown here as an example. So here I have two Gaussian probability density functions, and one of them I fix. So this one has an expectation parameter of 0 and a variance parameter of 1, and the other one I vary. Yeah. And now, first here, I vary the other one very little as compared to that. So the expectation parameter is minus 0.2, and the variance parameter is also just a little bit smaller than this one. So they are largely overlap. And the corresponding KL divergence, which I think is here, should be Q and P and not P and X, sorry. Is fairly low. So on the x-axis you see here the KL divergence. On the z-axis you see the divergence. On the x and y axis you see the parameters of the second univariate Gaussian, because it's all with respect to standard normal Gaussian. Now, if you change the mean of the second one, so the red one you can see much clearer now, has the different mean but the same variance, you get a larger KL divergence. Sorry, and we are here. I also have to look a little bit. Yeah, we are here. So shifting the mean makes quite some difference. So here the means are the same. Now the mean of the second one is 1. The variance is the same. The variance is still 1. So we get here. So this yellow greenish dot corresponds to this. So we have a larger KL divergence. They look different. That's the main point. Yeah. So if the probability density functions look more different, then the KL divergence gets larger. And here we keep the mean constant and look at the KL divergence, and it's again larger. So the minimum of this two-dimensional surface here is there. Here it's a little bit larger. So that's the KL divergence. Of course, the KL divergence is defined as this integral. Now, if we have, for example, these Gaussians for probability density functions, one can solve this integral analytically, and then one gets the KL divergence as a function of the parameters of the probability density functions. If one has probability mass functions, there is a corresponding definition of the KL divergence for probability mass functions, which involves then sums. There one can actually, if it's a non-parameterized probability mass function, just sum everything up. Usually when we're dealing with densities, we have formulas for the KL divergences, which are formulas that depend on the parameters of the respective densities. Yeah? KL divergence, questions about KL divergence. So important thing is it's 0 if the two densities that go into it are the same. It's larger than 0 if they are different. If they are more different, the KL divergence gets larger. They are less different, the KL divergence gets smaller. Everything else then depends on, of course, the specific densities one puts in, and it's hard to make general statements about. Now, with this definition of the KL divergence and this notion of a dissimilarity between distributions, the definition of the elbow and this decomposition follow almost automatically. So this shows, this is the proof of the log model evidence decomposition, and or a proof that I give here, and it starts with how the elbow is defined. So the elbow is defined like this. Then we can, here, this joint distribution, we can split into a marginal distribution of the data and the conditional distribution of the latent variables. Then we have here the log, and this is what's, if you learn about variational inference, what you have to get used to a lot, or what happens a lot, is that the products inside a log function can be written as sums of the respective arguments of logs, and that Riemann integrals are linear, so that you can, if you have then a sum of logs under this, in this case, the log of px time the log of px plus the log of pzx divided by qz, you can take the integrals apart. Yeah? So this happens all the time in variational inference, these basic foundations. So log turns multiples into sums, and sums of integrals can be split. That's the whole trick, essentially. So we can split this integral into these two integrals. And then here we have the log of px integrated over z. So ln px is a constant with respect to qz, so we can take it out. Then we have to integrate over qz, which is a probability density function, integrates to 1, so we have log px. And here we have another thing always happening, that if you reverse the order or if you reverse denominator and numerator inside the log, this corresponds to minus the log. So if we change that, then we are already at the KL divergence. And so we have elbow equals ln px minus KL qs. So we can put KL on the other side, and then we have this evidence decomposition. So the main point is this evidence decomposition works because the elbow definition works, and of course the secret behind that is the definition of the KL divergence, which means that if we define a different dissimilarity measure with similar properties, that it's 0 for if it's the same densities, and larger than 0 for other if they are not the same, then we can also define non-KL divergence elbows and do the same thing like variational inference without the KL divergence, but a different dissimilarity measure. So the secret, or one of the most important ingredients, of course, of variational inference is the KL divergence. But variational inference is not restricted to using the KL divergence. And there are papers about using non-KL divergent dissimilarity measures, and hence other forms of elbows, so that this log model evidence decomposition still holds. Yeah? Art was very interested in different divergences at one point. I don't know whether he wanted to discuss that with me at one point. But KL divergence is still heavily used, and whatever. I don't really have much of an opinion on that. I haven't really. I mean, of course, it would be interesting to see whether certain things are better if you use a different dissimilarity function. You can, in principle, and this definition, because you can, you can spend 10 years, or you can spend a long time thinking about this definition. and maybe there are better ways to think about this definition, but the way I think about this definition is that you want to do log model evidence decomposition, you have the KL divergence. Well, then if you define it like this, the log model evidence decomposition works. If you define this differently, you would define this differently, you would have a different log model evidence decomposition. Yeah. Good. Questions about this log model evidence decomposition at this point? We haven't really talked about what we need it and what it's useful for, but just this understanding. No, good. Now, why is it called evidence lower bound, elbow? Because it's a lower bound of the log model evidence. And by this we mean that the evidence lower bound, that's a typo, that's QZ. I have to get used to this X and Z because I am used to look at Y and theta, but we have always had data as X, so we should also have data as X here, and then our latent variables are Z. So the evidence lower bound as a function of the variational distribution over Z is always smaller than the log marginal likelihood. Why is this so? Essentially just because the KL divergence is always larger or equal to 0. So if you have this decomposition and you add something positive to the elbow, then to get the log model evidence, the log marginal likelihood, then the elbow must be smaller, or if the KL divergence is 0, equal to the log marginal likelihood. Yeah, so this is always positive, hence this must always be a little bit smaller than this, or if this is 0, then they are the same. Yeah. And this is the evidence lower bound property of the elbow, and it just follows from the positivity of the KL divergence. This is a visualization. So for a fixed data set X, the log marginal likelihood, also called the log model evidence, is a fixed scalar quantity, and the size of this quantity I draw here as the bar. Now, what we've seen is that we have that we can decompose this bar, this number, so for example the number 10, into two numbers, for example 2 plus 8. And this number is always positive, so this number is always smaller or equal to than this number. That's the importance of this decomposition, together with the positivity or non-negativity of the KL divergence. Now, based on this, we already can talk about how to now use variational inference to solve the how to use this to solve the variational inference problem. Because we can do two things. One thing we can do is we minimize the KL divergence with respect to QZ. So QZ was arbitrary, so we can play with it. We can, for example, if it has parameters, we can change its parameters. And if we try to minimize the KL divergence of QZ between PZ given X, so the conditional or the posterior distribution, then of course, if we minimize the KL divergence, what we are doing at the same time is that we make QZ more similar to the posterior distribution. So we approximate the posterior distribution by minimizing this KL divergence. At the same time, if we make this smaller and smaller, this elbow thing gets larger and larger, and the elbow becomes closer or more equal to the log model evidence. Yeah? So that's the one way to view variational inference. We minimize the KL divergence with respect to QZ. PZ of X, this is what we don't know, and what we're trying to approximate with QX. One thing, if we are in a scenario where we can actually compute the posterior or calculate the posterior distribution, like for example in conjugate cases, then of course for QZ we can just take the true posterior distribution. So we put in PZ given X as QZ, then the KL divergence is 0 immediately because they are the same thing, and our elbow is equal to the log marginal likelihood. Yeah. So in this sense, exact inference is a special case of variational inference, because if you can evaluate this analytically, then you essentially don't need the whole variational inference business, and you can think that you're still doing variational inference by putting this in here and so on. But yeah. But that's the special case. Now, some authors emphasize this minimization of KL divergence more. Most standard forms is actually viewed differently. So instead of minimizing this part, we are maximizing this part. Yeah. So if we increase the elbow, so we take this division here and push it in this direction by changing QZ. What happens is, of course, that the KL divergence again gets smaller, so QZ gets closer to the posterior, and at the same time the elbow becomes closer to the log marginal likelihood. And this way of doing variational inference, this is in some way the more common way to think about things. So we want to maximize the evidence lower bound with respect to the variational distribution. This has two consequences. First, the elbow gets closer to the log marginal likelihood or the log model evidence, and because it minimizes the KL divergence, this arbitrary variational distribution gets closer to the posterior distribution. Yeah. Good, and this is a good time for a break. Any questions? We will see this again in a second. Maybe it gets a little bit clearer then even, but with a little bit more in a more dynamic fashion. But otherwise, any questions for now? No, then let's have a break and continue like 1:15.